Once again, good morning, everyone, and welcome back. This is our second session on the Environmental Bioethics course. As always, we begin with a little prayer. In the name of the Father, the Son, and Holy Spirit. Blessed Trinity, we love you, we adore you, and we thank you for your many blessings, for the gift of life, and for having us here once again today. We ask your inspiration as we seek to understand the nature that surrounds us and our own human nature, so as to protect it, preserve it, and promote it among those who surround us. We ask your blessings upon all our efforts and all your children throughout the world. In the name of Christ our Lord. Amen. All right, so we're going into now, if you recall from last lecture, we were looking at the formation of the Earth first, all the geological developments in 4.5 billion years to the planet that we have today, from a ball of fire, essentially, condensing and cooling toward the crust enough to have liquid water and allow for the possibility of organic life as we know it, yes? Then the Earth biosphere, which is the living aspect of Earth, has three components, if you will, or this life happens in three regions. The lithosphere, which is the actual crust, the land mass of the Earth. Then there is the hydrosphere, which is the water liquid component, mostly the oceans, which is about 3/4 of the Earth's surface. And then the rivers, lakes, and other water bodies, natural water bodies. That's the hydrosphere. And then there is the atmosphere, right? The atmosphere is a gas, but gas is also a fluid. Just like water is a fluid, liquids are fluids, and gas are also fluids, but gas are much less dense fluids, so we don't really see it, but we can actually feel it. If you move your hand hard enough, you feel a little bit of wind resistance, and that's because we're actually cutting through a fluid that is gas, which is the atmosphere. Okay, all right, so as a fluid, it will have the fluid dynamics that all fluids are subject to, those physical properties. And we're going to look at some today, especially in the formation of weather, how weather happens on the planet. Yes, Michaela?
Is frozen water also part of the hydrosphere, or is that something else?
Yes, no, it is. It is.
Okay.
Because certainly it is water, though in frozen state, but even that has not precluded animals from living there, namely the poles. All right, so it's very interesting how I say that life is tenacious, right? One of the characteristics of life is that it's tenacious. In other words, if there is a surface, if there is an area, most likely it will be populated sooner or later by some living species. Okay? Even if we abandon cities, let's say hypothetically, I don't know if you remember back from a few decades ago, at the height of the Cold War between the US and the Soviet Union, one of the war developments was the neutron bomb. You remember the neutron bomb? Ever heard of it? Okay, the neutron bomb actually kills life, but leaves the structures intact. So it would kill the people inside the city, but would not destroy the city. Reverse from conventional bombs, right, that destroy whatever is in sight. And it was really considered unethical to do that. But if hypothetically we would evacuate all cities or just one city from people, but leave the structures in sight intact, what do you think would happen over time? If you fast forward a dozen years, 100 years, 1,000 years, with weather occurring, all right, and climate, rain and humidity and wind and so forth. What do you think would happen? Yeah, it would start, eventually the artificial structures will start crumbling because of erosion, weathering, what we call weathering, right? From wind and water combination. But also in the meantime, organisms will start taking over. And you start first with microorganisms, for example, algae, bacteria, fungi, lichens, which is a combination, it's a symbiotic relationship between algae and fungi. Will continue to erode because lichens actually pour out acid, which further dissolves the rock, all right? And eventually the buildings will start collapsing and life will start occurring, and you would eventually get a forest with all ecosystem. And in fact, we have evidence of that. We go back, what do we have? The ancient civilizations, the ruins of ancient civilizations. In Latin America, you walk around, mostly in Central America, you walk around the jungle and you see these mounds of forests, and you have huge trees growing on top of these mounds. Underneath that mound is going to be typically a pyramid, okay, which is all crumbled stones. And there is a mound on the whole trees. I've seen this live, huge trees growing on top of that. So nature is tenacious, and if there's a surface to be colonized, the chances are, the probabilities are that it will be colonized. Mm-hmm. Okay, so let's get into this now. We're going to look at the atmosphere, and then next lecture we'll look at the hydrosphere, and then we'll look at energy transformation, and then we're going to look at finally the bioethical analysis, precisely because of the claim of climate change and global warming and such. So we're setting the stage and giving you the scientific background to be able to analyze climate change, all right, and global warming, if it's happening, how much of it, and so forth. Okay, so the atmosphere is layered, okay, it's layered. And the most interesting thing that some people don't realize, the atmosphere has weight, and that makes for the pressure, atmospheric pressure. We'll get to that. But first, let's look at these layers. So in addition to the layers, we're going to look at the composition of air, the physical and chemical composition of air, barometric pressure precisely, and then finally wind patterns and storms. How does climate and weather happen? So in a sense, it's a little bit of review of your high school earth science course, if you ever had one. But these are the layers. They're basically 5 layers starting from the surface of the earth upward and out. In a sense, it's a continuation from the crust, if you will. We started at the core, and we looked at the inner core, the outer core. Then we looked at the mantle, lower mantle and upper mantle. And then finally, we hit the crust. Now we're going to go beyond the crust, okay, in continuous layers. Because of a sphere, then everything's going to layer around the sphere, right? A little bit like the onion. So the first one is called the troposphere. The troposphere is where life exists, as we know it, the troposphere, which is approximately 10 kilometers. So it's a nice decimal system. It's about 10 kilometers up, all right? In miles, how much is that? It's 1.6 kilometers, so it's a little more than half, so about, I guess, 6 or 7 miles, right? 7. More than 5 and less than 10 miles. So kilometers are 1.6 kilometers per mile. Anyway, get used to the decimal system and the metric system. Then another 40 kilometers, and you have the stratosphere, okay, the stratosphere, where most of the phenomena that we observe are occurring, including the high cloud formations and all that. That's up to 50 kilometers. And then approximately another 50 kilometers, more or less, it's a kind of a large boundary there, is the mesosphere or the middle sphere. You notice of the 5 layers, this is the middle one, mesosphere. The air is getting thinner and thinner, all right? That, when I say thinner, what property am I looking at? What physical property? Density, right? What is the most thickest density? The solid state. Then liquid is less dense, and then gas is less dense again, but density, which is a ratio of mass to volume, all right? the more mass in a particular volume, the more dense the object is. So you have the three states and the transition of the three states from solid to liquid to gas. All right, this is all gas, but it still has density. So the denser, where is the denser air or the denser atmosphere? Close to the surface or further away from the surface? Which is more dense? Yes, but the question is, why is it so? It is true. And what is it causing that density to be at the troposphere? Okay. Then we get into the thermosphere, which is very thick or very, not thick, I mean, long, if you will, or wide. It goes from about 100 kilometers to 500 kilometers. And then finally, we get out into the exosphere, which is the final transition layer into outer space or into space. All right, so again, troposphere, where life occurs, then stratosphere, most of the weather formation up until that level, mesosphere, middle layer, transition, thermosphere, starts getting very cold, and then exosphere, the transition to space. Here is a little caricature of what happens in some of these different layers. They're not to scale, of course, okay, not to scale, but in the troposphere, we have most of the phenomena that artifacts that man has generated. Most flight occurs within the troposphere. Airplanes, jets go to the limit here, the boundary. What do you think is the limit factor for airplanes to get up to that height? Think of, so the airplane needs to be moving right at some distance, some speed, so it doesn't collapse. And to move, it needs some propulsion. You know how hydrodynamics work? What keeps a wing afloat? Through the fluid of air. Precisely, where an airplane, we can say that it is literally sailing through the air, all right? And the basic idea of a wing, to keep a wing afloat, is to move the air underneath faster than the top, okay? And that's part of that's why wings tend to have that concave shape. That's part of it. But the other part is that one needs some speed underneath the wing to be faster than the top of the wing. So birds do that by what? By flapping, which is in slow motion. It's kind of a pushing and pulling motion, okay? Birds do that by flapping. Planes do it by what? Either propeller or jet, but basically moving the air underneath the wing faster than the top of the wing. So it's the same basic principle. And so when we talk about motors, typically it's a combustion motor, right? So therefore it needs oxygen to a certain degree to have the combustion done. And that's why it cannot go too high, because it's going to run out of oxygen. Unless it uses other types of fuel, which could be solid fuel and stuff like that, which doesn't need oxygen for combustion. And that's why other artifacts can navigate in the thermosphere and even in space, because their motors are not using, it's a different type of it's not actual combustion. I'm not sure exactly, but it doesn't involve oxygen, right? Okay, so let's move forward into the more important stuff. These are the different phenomena, excuse me, occurring between the troposphere and the stratosphere, which is our concern, is mostly the troposphere, again, the upper 10 kilometers, and particularly the cloud formation and the cycling. We'll look at the different cycles a little later on in some of the lecture, but basically the water cycle. We can start on the ocean, at the surface of the ocean, evaporation, and then migration of the clouds into land. As that water vapor moves into land, it tends to condense. And as it condenses, it precipitates, rainfall, and then eventually with river runoff back into the oceans or lakes, and you have that cycle repeated. So that's the water cycle in brief. Most of the cloud formation happens within the troposphere, especially the cumulonimbus clouds and the ones that are heavy with rainwater, okay? The transition between spheres is called a pause. So the transition between the troposphere and the stratosphere is a tropopause. And then between the stratosphere and the mesosphere, what do you think that name is? I'll give you the first half. Stratopause, okay? So the pause is a transition between one sphere and the next. And of course, this boundary is not sharp. It is a diffuse boundary. It's a gradient, but it's definite, and it hangs around more or less around the 10 kilometer around the Earth, which is the highest peaks are at that height, Mount Everest here in the US. Okay. Oh, lastly, notice the temperature climb here, all right? Here is 0 degrees centigrade, 20 degrees centigrade, which is on the cool side. It's probably in the 60s Fahrenheit. But it's on the cool side, but livable. It goes right through 0, and the temperature drops fairly fast going up away from the surface of the Earth because of radiation, right? Radiation is dissipating. And so by the time we get to the tropopause, it's below 0, between minus 20 and minus 40 degrees. So definitely water is freezing up there. And that is precisely these high clouds called the cirrus clouds, the stratosphere. They're little like pencil scratches, okay? They're very high clouds. It's actually crystals, water crystals that are way up there and are reflecting the light one way or another. So they look like little pencil scratch, pencil marks. That's crystallized water up there, okay? And then it maintains that thermocline of about 40, minus 40 to minus 50, and it keeps dropping as we go into outer space. Yeah, question. Yes, I'm not sure. I didn't have time to look it up, but that's a good research question there. You can punch it in and find out. It's some kind of a light phenomenon that is occurring, some kind of a ray phenomenon that that is occurring through the stratosphere. Okay, I don't know if it's associated with the aurora borealis, that curtain of light of sheen that occurs in the poles. Notice that the ozone layer, by the way, is up here. And what's the chemical composition of ozone, by the way? O3. Okay, so it's an extra oxygen that is unstable in the troposphere, because what's the normal composition of oxygen in the troposphere? What we call diatomic, O2, right? 2 atoms of the same element, O2. Just like nitrogen, for example, which we'll see in a minute, the composition, N2. And that's stable at this temperature and pressure. But when it gets that high, then a combination of less temperature and less pressure, O3, is stable up in this area. And what is significant about the ozone layer vis-a-vis life on Earth and mutation rates? I'll give you the hint of mutation rates. What do we want to filter out from the sun to minimize, UV, ultraviolet radiation, which penetrates and can even penetrate the skin and cause mutations. Well, we know skin cancer and other types of cancer, all right? So the ozone layer filters out UV. And that was a big issue of the ozone hole in Antarctica that developed a few years ago, and now it's closing up again and so forth.
So it says they're not really even sure what blue jet.
Okay.
Blue jet.
All right.
It says splashes of light that occur above thunderstorms and are associated with the normal lighting in the thundercloud below. It says the causes of the phenomenon are not known.
Wow, fantastic. So it's kind of it's a lightning but going up instead of down. And then the color is different. Obviously it's a blue color. Never seen one. Oh yes, it's an ionization. Okay, so it's an energy transfer of some sort of large magnitude, right? Probably very fast. So similar to a lightning, but going up instead of down. Interesting. Okay, let's look at the composition of the atmosphere in the troposphere. All right, in the troposphere, very important to say what layer we're at. The one that interests us for life is the troposphere. This is the atmospheric composition. We're building up a case for why is the air layered? Why is gas layered around this globe that we call Earth? And why doesn't the atmosphere fly out? Since it's a fluid, fluids don't hold their own volume, right? In contrast to solids that hold their own volume, that's one of the characteristics of fluids, that they don't hold their own volume. They hold the volume of the container, liquid and gas. Okay, well, let's look at the percentage concentration of the atmosphere of the air that is in front of us right now that we're breathing in and out, by the way. It is mostly what? Nitrogen. N2, diatomic. Okay, so stable, 2 atoms of nitrogen form a nitrogen molecule in gas. So in its natural state, nitrogen is a gas. And it's most of the atmosphere, it's almost 80%. Okay, almost 4/5 of the Earth's atmosphere, of the air in front of us, is nitrogen, diatomic, N2. The rest is mostly oxygen. Thanks be to God for that, because we need it for breathing. Again, diatomic, O2, little over 1/5, 21%. Then we got 1% left, right? Because 78 plus 21 is 99. We got 1% left. Look at all the stuff that is packed into that 1%. Of that 1% is mostly argon, which is another element, Ar. Okay. And so that's 0.9% of the 1%. Of the 0.1% that is left of the Earth's atmosphere, the air right in front of us, 0.1%, not 1, but 0.1%, okay? 1/100th of the volume has all these other gases within. Gases. Neon, which makes, right, neon gas makes those lamps. Helium, light, makes the balloons rise, very, very light. Methane, which is combustible. And it's also a byproduct of digestion, as we well know. NO, nitrous oxide. Ozone, the O3. But it is mostly carbon dioxide, CO2. So that 1/100th of the atmosphere is mostly carbon dioxide. So almost 0.1, no, 0.09. We round this off. They give you 3 centésimals here. You can round it off. 7 makes this 0, 5. So it would be, if we round this number to whole numbers, it would be 94%, okay? Almost 95, almost. Most of this trace elements is mostly carbon dioxide, but that's only 1/100th of the volume of the air in front of us. And that's a good thing, because if there was more CO2, we would basically pass out. We couldn't maintain life, all right? However, there are other creatures on Earth that need this desperately to live, which is plants for photosynthesis, right? Now, do plants need oxygen? No? We can keep plants in a vacuum or just feed them CO2 100%?
They still have mitochondria.
Yeah, so if the plant is alive, then the plant is the plant is metabolizing. And if there's metabolism, ATPs are being burned because there's cellular metabolism going on. And therefore, plants do respire, plants do breathe, at the cellular level. In fact, the stomata, it's all about allowing air in and out. So if the plant is alive, the plant is also metabolizing, respiring, breathing, and therefore it also consumes some oxygen. But it is producing more oxygen than the one it consumes through the process of photosynthesis. Unlike us, that we certainly consume oxygen, but we don't produce oxygen because we don't photosynthesize. Okay, but just because plants and algae are undergoing photosynthesis doesn't mean that they don't use up air. They certainly do.
So the first plants on Earth, did they create their own oxygen?
Okay, very good question. Before the plants, there was what? Yes, the phytobacteria, right? The phytobacteria, which were before classified as algae, but now it is known that they were bacteria, and they had the pigments necessary for photosynthesis. But because they were bacteria, I don't even know if they were anaerobic or not, okay, but they certainly needed very little, if any, oxygen. There was some oxygen, but very little. It was mostly a toxic environment, but that was the key thing. And they became so abundant, so for whatever reason, that environment was conducive for them at that time. But in their abundant production of oxygen, they actually changed the atmosphere big time into 20% oxygen, okay? Which allowed then for other life to come in. And that's what we see. Nature is also repetitive and economic. In other words, let's say that the photosynthetic mechanism was generated in this phytobacteria. Cyanobacteria, I was trying to look for the word because phyto is a reference to plants, cyanobacteria. And it worked. And so that stayed on. And the theory, the prevailing theory, remember the protosymbiont, is that these cyanobacteria at some point were incorporated into other organisms, and the photosynthetic capacity was maintained, which eventually would evolve into the chloroplast of plants, the chloroplast of true plants. Interesting. Conversely, there was another set of biochemical pathways that was metabolizing, that was using up and recharging ATPs, which eventually became the mitochondria, right, which are two major organelles in plants, and of those, only the mitochondria are in the animals and fungi. Okay, so back to here, a couple of things. First of all, most of the air that we're breathing in and out of our lungs is nitrogen. And what happens? Well, nothing happens because nitrogen in its gaseous state is known as inert, meaning it only goes in and out of the lungs and is not substantially absorbed by the lungs. So nothing happens. We only need 20%. That is even, we only actually use up a fraction of this 20% of the oxygen that comes into our lungs, right? So we don't really need 100% oxygen. It normally is an overabundance of oxygen. Okay, that's when the lungs are not working properly at all. But the nitrogen is known as inert, meaning that it comes in and out of our lungs without affecting us. Thanks be to God. Otherwise, we'd be in trouble because under high pressure, nitrogen actually goes into the system, like in the case of scuba diving, right? Under pressure, underwater, and that nitrogen then does diffuse into the body and to the brain. And what effect does it do on the brain? The nitrogen, when nitrogen gas does hit the brain, it's a sensation equivalent to being drunk. And in fact, it's called nitrogen narcosis. And if you're scuba diving down there at 2 or 3 atmospheres of pressure, you may be 60 or 100 feet below water, you don't want to be drunk down there. You want to be very alert, okay? And so it's an issue to deal with in diving and deep water diving. Okay, so that's very interesting about the nitrogen, just comes in and out, no problem. But this is the one that we use. And then we exhale, so we inhale the oxygen at the cellular level. It's actually that oxygen is absorbed by the capillaries into the RBCs, red blood cells, because it combines with iron. Iron, the core of the RBC is an iron molecule. And when the oxygen combines with the iron, what does it do? FeO2, Fe for ferrum, for iron, it oxidizes the iron, okay? Iron oxide, otherwise known as rust. And when we look at rust, in a rusty piece of metal, looks kind of reddish. And that's why the blood looks reddish, okay? Because it's the iron that has oxidized in it. And then the collagen also gives it a particular taint and so forth, the proteins that surround it. But that's oxygenated blood, which is arterial blood, which is going into the tissues. The return blood, also known as venous blood, going back to the heart and then being pumped to the lungs. The exchange, what happens at the capillary level of the organs? Oxygen gets off, and what gets on? CO2, carbon dioxide, which is a byproduct of cellular metabolism, right, of recharging the ATPs in the mitochondria. And so that CO2 is picked up by the RBCs, going back to the heart to be pumped to the lungs, and from the lungs at the alveoli, CO2 is released. Small amount, but significant enough to maintain this level, of 1/100th of a percentage, because then the plants are going to need this big time. And I'm just kind of setting up the an argument here, kind of a counter argument, that an increase in general, a slight increase in CO2 in the atmosphere would not necessarily damage us by breathing, us meaning animals, all right, because we don't, there's still a very significant amount of oxygen in the atmosphere, but would actually benefit what? Plants. Plants would benefit from an increase in CO2. The side effect of having CO2 in the atmosphere is that it tends to retain heat, all right? It has a high heat capacity, and then it causes an effect called the greenhouse effect. So it tends to accumulate heat instead of the heat dissipating into the atmosphere. And that has its own consequences of melting of the poles and so forth. So that's the issue about the CO2. Okay.
But doesn't also, plants can only photosynthesize to a certain capacity of carbon dioxide, and then it just photosynthesizes.
That's right, because then the chloroplasts are going at its maximum rate, and any more CO2 is not going to be used. What it could promote is more vegetation as a whole throughout the earth, okay? Because then you're giving it all the maximum food, if you will, or nutrient all the time, okay? Now, so all this to say that these are, what are these? What are they? Yes, and gases are composed of what at the molecular level? Just gave you the atom. Molecules, atoms, okay? Matter. So matter matters. Matter matters because all matter is affected by the laws of the fundamental laws, the four fundamental laws, all right, or forces. And the one that is most applicable here at the macroscopic scale, not micro, because remember micro, you have the strong and the weak force that are keeping the atom together. But the other two forces, all right, one of those two significantly affects these molecules, these atoms, this matter, which is going to be gravity, the force of gravity. Originating from where? The core, the inner core, that solid ball of iron that is white hot, but aside from the white hot, is also exerting a tremendous amount of gravity, okay, of pulling, which is kind of mysterious. What does gravity mean? Well, it's a force. Yeah, but what is a force? What is a force? Why would things tend to coalesce? To me, it's a big mystery. Why would things tend to coalesce, and come together? All right. So gravity is affecting these atoms, these molecules, and that's why the atmosphere sticks around. Theoretically, if we drill a hole through the Earth, the atmosphere would pour into that hole and continue on down. And if we could hypothetically make a hole all the way down to the iron core, the atmosphere would pour down into there, condensing more and more and more. And as that atmosphere condenses, it would actually go through the other states, because now it's under more and more pressure, and it will go from gas into liquid, and from liquid eventually into solid. Hypothetically, if we could somehow take away the heat dissipation that is occurring from the core, all right? If we could hypothetically imagine an iron core of the Earth that is cold, or at least room temperature, not hot, and generate a hole all the way down there, by the time these fluids pour down into that hole, they would go through the other two states of matter and predictably even become solid. So we have solid ice, we have solid oxygen, solid nitrogen, etc. Right? Because it's going through the states. Remember the gas laws. It's a combination of temperature and pressure. So the more pressure that we put on a gas, the more dense that gas becomes until it becomes liquid. If we continue the pressure, that liquid becomes solid. We're literally squeezing those molecules together. We can have the same effect with temperature, okay? But the inverse. The less temperature, the more the gas comes together into liquid, all right? That's what happens to water, for example. And if we continue to lower the temperature, that liquid will eventually become solid. And that's the ice cubes in the freezer. We're lowering the temperature. The pressure is the same because that ice box, that refrigerator, is at atmospheric pressure, right? It's on the surface of the Earth. But it's getting colder. So those molecules are clustering together. At any rate, what I want to point out from this is that the downward force of these atoms, the downward force of the atoms being pulled by gravity is what causes pressure, atmospheric pressure, which at the surface of the Earth is the standard 1 atmospheric pressure, okay? And it's known as standard pressure. In fact, it's known as standard temperature and pressure, STP, standard temperature and pressure. You see that acronym STP. That's 1 atmosphere pressure, and it can be measured by a anemometer or the machine that measures pressure. And the classical matter that is used for measuring pressure is mercury, okay? And it's measured in inches. And this is the magic number, 29.92 inches of mercury is 1 atmosphere of pressure. You know that mercury, which by the way is indicated as Hg because when it was discovered, it was thought to be, so what is the color of mercury? When I was a kid, I used to play with mercury. I love for yeah, it's very dangerous, highly toxic, okay? It can cause mutations and other deformities. But I love for thermometers to break. Not in my mouth. Yeah, yeah, the mercury thermometer right in your mouth. Yeah, it's a miracle that we're alive, okay? They can know it. Yeah. Yeah, right, exactly. And, well, we used to, yeah, and flash it like this to drive it down, and sometimes it would hit the counter. Oh, I love that because then I would gather the mercury and play with it for hours. Mm-hmm. Oh, yes, yes. Right, exactly. Now, of course, thank God they're made out of. It's a miracle we're alive. We used to play with mercury to no end. Absolutely. But I just want to find. It's a silvery color, right? And and it's a liquid. It's the only metal that is liquid in its natural state, right? Other metals typically are solid. And so originally it was thought to be silver, liquid silver. Yeah. And that's why argentum is actually, argentum is a name for silver in Latin, argentum. And that's why it's indicated with AG, okay, on the periodic table, number 47 there. AG, that's silver, argentum. So argentum is a reference to silver, and hydro is a reference to water or liquid. So liquid silver, hydrogyrum is the original name for Mercury, and that's why the letters Hg, okay? Anyway, little aside. Inches of mercury on the anemometer.
Worldwide?
Yes, it has stuck. It has stuck because that is the standard unit. So here's a little couple-minute video of a fellow explaining this. That was interesting. It's a young fellow. We'll have these links if you want to use them later on for your classes.
Hello, today we're talking about understanding barometer readings. And what we use to measure the air pressure is called a barometer. And essentially all air pressure is the downward force of the atmosphere. And when you have more downward force, the air pressure rises. When you have less downward force or less weight, the air pressure drops. And that's important because typically what happens is when the air pressure is rising, the air is sinking, it's putting more pressure on the earth, but even more importantly, sinking air clears out the sky. So generally you have nice weather when the skies are clear and the barometric pressure is high. When the barometric pressure falls, you have rising air. It's rising away from the surface of the earth, so the pressure that it's putting on the earth goes down, the pressure falls. And typically with low pressure, you have clouds, you have rain, and when you have extreme conditions, you can also have thunderstorms, sometimes severe. The lower the pressure drops, you also get.
Just want to mention briefly here that, so high pressure, low pressure, right? High pressure system, low pressure system. It's remember, heat rises, so hot air rises. As it rises, there's less pressure, there's less density because the molecules are expanding away from each other. And they cannot expand into the earth, so they expand up and out, all right? As they expand up and out, they start cooling. As they cool, they start condensing. As they condense, then they're going to start dropping because they're more dense, and now they're more reactive, if you will, to gravity, all right? But they cannot drop down at the same spot where the air is rising, so they're going to drop down sideways and start generating these, guess what? Convection currents, just like the mantle, but in the atmosphere. So we have a similar phenomenon with a much lighter fluid, but a fluid nonetheless. So again, convection currents, which is the basis of the weather system. Don't be confused. This air rising makes for low pressure, all right? Whereas, and then it starts condensing. So above, the condensation above is what makes the cloud formation, all right? That's humidity that is concentrating. So we may feel a lot of humidity and think that the air is heavy, thick, but no, but that's humidity. That has nothing to do with the air pressure itself. That's low pressure, okay? As the air comes down, then it's high pressure, but as it is coming down, it is clearing the atmosphere from above, and therefore is clearer skies. So that part is, at least to me, is counterintuitive. In other words, a cloudy day, I tend to think as heavy, but no, it's the opposite, it's high pressure. Whereas a clear day, say in the desert, a clear day, you know, those Arizona days of clear blue, used to go to, my brother and sister lived in Colorado, and they have these blue days, very dry, but that's actually high pressure. the caveat to that, or the little side note to that, is that Colorado is actually a mile high, so it's thinner air. Okay, the Mile High Stadium, it's 5,000 feet above sea level, so that's an altitude issue, which is different. But at sea level, it would be high pressure. Okay, continue.
The worse weather, for instance, the lower the pressure in a hurricane, the stronger the hurricane is. So understanding how to measure it, we use these barometers. And it's very simple to read a barometer to tell you if the weather's going to turn good or bad, or whether you have high pressure or low pressure. Standard pressure, kind of the average pressure, is 29.92 inches of mercury. That's the way we measure it. That's the way it's marked out on most barometers, whether it's a mercury barometer, a water barometer, or an aneroid barometer. This type is an aneroid barometer. When the pressure rises, the needle goes up. And if you measure it against 29.92, anything above 29.92 is considered high. The closer you get to 30 or 31, considered high. And the farther below 29.92 you go, the closer to 29 or even below 29, that means the pressure is low. So simply watch it, engage it against that 29.92 inches of mercury. Above it is high, below it generally is considered low.
Introducing the new Glad Force lexicon.
Okay, so that's the basis for the weather system throughout the world, and now we have a closer understanding on how hurricanes actually form, at least from the pressure aspect of it. Okay, it's a high pressure system versus a low pressure, but then the other component of the hurricane that we need to understand is the actual twirling, which is what's causing the damage, because that's going to translate into winds moving horizontally on a plane and in a circular motion. Now we're going to shift gears a little bit so you understand about pressure, atmospheric pressure, right? Essentially, it comes down to the weight of the atoms of atmosphere that we have on top of us, literally pushing down because of their reaction to gravity. Let's look at heat now. Let's look at heat. How does heat form on the surface of the Earth? And why is it warmer at the tropics and the poles, right? Or why is it colder in the poles and warmer in the tropics or close to the equator? A little bit of geometry, and when we get into ratios, it's also the basis for probability theory. So again, think a little quantitatively here in preparation for the next stop of this bus. To compare the size, first let's look at size. So this half circle here represents the sun. And this little blue dot, can you see a little blue dot there? Okay, that represents Mother Earth, all right, Oceania. The ratio of diameter, distance across, okay, the longest distance across a circle is about 100 to 1. So, you know, then this means that the diameter of the sun is 100 times larger than the diameter of the Earth. And this is more or less to scale. Okay, if the sun were this size, the Earth would be this size. That's 100 to 1 scale, more or less. That's because I could make that little blue dot smaller. But that's about 100 to 1 ratio there. However, the distance is a different story. Okay, this is, if we were at this distance to the Earth, we just simply wouldn't be anymore. We would evaporate, annihilate, and disappear from the universe if we were at this distance to the sun. Okay, it's absolutely way too close because of the intense heat that is happening. I mean, this is one big, huge nuclear reaction that is occurring here on the sun. It's a gas on fire. It's mostly hydrogen ball gas on fire.
What if the Earth would be a little bit further away? It would burn up.
No, well, at this distance, this is not to scale, is what I'm saying. This is not the distance from the Earth to the sun. I'll tell you what the distance is. This is just to show these two balls, how they compare in size. This is a size comparison. And I'm telling you here that if the sun were this big, the Earth would be this big. Okay, exactly. In other words, very, very tiny. In fact, the 4 inner planets are tiny compared to the 4 outer planets, if you look at the scales. But how about the distance? Okay, again, using the diameter as a parameter, as a standard, okay? How many diameters are we away from the sun? How many Earth diameters? So if we look at the diameter of the Earth, which would be the longest distance of this little circle, all right? The longest distance, you understand the diameter, right? It's a line that goes across a circle through the center of the circle. It's the longest distance inside a circle. That's the diameter. Radius being half of that. So the radius is this, okay? Okay, so if we were to use that as a standard, how many diameters, how many Earth diameters, what was that, what's the diameter of the Earth? The radius was 6,000, no, kilometers? Look it up from my, I think it was 6,000 kilometers, the radius. So the diameter would be 12,000. Or miles, doesn't matter.
Was it 24,901?
24,000 miles?
Yeah. Or maybe, no, that was the
Okay.
circumference, I'm sorry.
Circumference, no. So that's 3 pi,
It's almost 4,000 miles.
4,000, so it's about,
3,959 miles.
okay, so it's about 6,000 kilometers, I think, more or less. All right, so that's the radius. So diameter would be double, right? 12,000 kilometers. If we were to use that as a standard, in other words, how many Earths would fit from here to the sun? Right? Exactly, 10,000. 10,000. If we were to line up, you know, how far away are we from the sun? 10,000 Earths. Approximately. This is whole numbers, okay? That's why I have the wiggle, approximately. Yeah. That's right. Yeah. Okay, yeah. All right. But the idea is to get a proportion, okay, to get a grip on this number, to wrap our minds around it, like they say, if the Earth were here at this size, I'm sorry, if the sun were here, right here on this screen projection, and this Earth were this size, where would this Earth be? Going that way, beyond the gate of the entrance of the university. That's where the Earth would be in proportion. Okay, way out there. That's the outfield for sure. Okay. So that would be where the Earth would be if the sun were this size. So we are in lay terms, we are a humongous distance away from the sun, thanks be to God, because if we were just a little closer, like Venus, there would be no liquid water, everything would be boiling hot. And if we were just a little further away, it would be so-called, like in Mars, everything would be frozen. Again, solid ice, no liquid water, and therefore no life again. So we are just at that right distance, which is very far. We got to keep the sun very far away. And that's why we can see the sun as a little dot, basically. We get closer, it's going to get huge. But what I'm trying to say is that at that distance, what affects us most is the light of the sun, not the heat of the sun. Okay? And certainly, it's not going to make a difference the curvature of the Earth. So some people think, well, because the equator of the Earth is closer to the sun than the poles. Yes, but it's closer by a fraction of a fraction of a fraction of a fraction, okay? It's not significantly closer. Mathematically, yes, the equator of the Earth is closer to the sun mathematically than the poles, right? Because it's a curved surface. But it's not significantly enough to make a temperature difference, is what I'm trying to say. The temperature difference is rather because of the angle of incidence, what is known as the angle of incidence of the sun rays. So let's look at that. Prepping you up for the next little video. This is the angle of incidence. Now, this blue ball represents the Earth. Okay? Now, a tangent a tangent, and the red rays, the red arrows represent the sun rays coming into the earth, all right? So for all practical purposes, since the sun is 100 times larger than the earth, because the sun is 100 times larger than the earth, look at this, just look at this area over here in front of the earth, okay? For all practical purposes, the sun rays arrive to the earth almost parallel. Of course, it's a radial pattern, right? The sun rays is a radial pattern. In other words, the sun rays are going out of the sun in a spheric fashion. So it's a radial fashion. But because the surface of the sun is so much bigger, it's 100 times bigger than the surface of the earth, the rays that come out of the sun, the fraction, the very small fraction of rays that come out from the sun to hit the earth are considered to arrive here practically parallel, almost parallel. There's a slight angle to them, of course, but that angle is so narrow that it's practically a parallel. It's almost like, if you will, a cylinder of rays coming from the sun to the earth. All right? Understand that concept? You can picture it? Now, let's go a little further. So that's why these arrows are essentially parallel to each other. If there were another ray coming through here that misses the sun, misses the earth, then that light ray is gone. It's not going to hit the earth, right? And so the same case down here. So it's a very narrow range of rays from the sun that actually hit the earth. Only what is essentially the circumference or the circle of the earth. All right, now, you know what a tangent is in geometry? Remember geometry, a tangent is a straight line that only intersects the surface of a circle known as the perimeter, right? At one point, a geometrical point. So again, the tangent is a straight line that intersects, that touches a circumference at one point. Want to picture in your mind a ball and a coin, right? You can move that coin around the ball, and if the coin is flat, it's only touching the ball at one point because the coin is flat, all right? So the coin represents the tangent, if you will. You good? All right, now we have a little bit of geometry. You have the rays coming in parallel, hitting a curved surface, right? And the angle at which it would hit a tangent on that point where it's touching is called the angle of incidence. That's the angle of incidence, illustrated here in the lowercase a, letter A. These are the angles of incidence. So for the rays that are closer to the poles, you see that the angle of incidence is large or small. This angle of incidence, small, right? A1 is a relatively small angle, you see. Is that larger than 90 degrees, for example? No, it's less than 90 degrees because 90 degrees is perpendicular, right? So it's less than 90 degrees. These are the incident rays because they're coming in. Incident rays are coming in. And so the angle of incidence is the angle that is formed by an incident ray to a tangent projected on the surface of the earth or the surface of a sphere. As we move closer toward the equator, which would be here at the middle, right? As we move closer to the equator, the angle of incidence, does it become smaller or larger? Larger, you see, because the tangent now is rotating, if you will. The tangent is rotating and is moving its angle toward the equator, all right? At the equator, that tangent is going to be perpendicular to the radius. Well, it's perpendicular to radius everywhere, but at the equator, it is vertical. It is vertical, all right? on a flat equator. You know, our equator is slanted, but just consider a flat equator, horizontal equator. So you can see that as those rays, the rays that are hitting the Earth closest to the equator have a larger angle of incidence. So we can do this simple relation here of the three angles of incidence, so that the angle of incidence closer to the equator is larger to the angle of incidence closest to the pole. If we extrapolate in both directions, let's extrapolate toward the pole itself. At the pole, a sun ray that just skims the pole would have what kind of an angle of incidence? It would approach 0. It would approach 0 what? What's the units of the angle? Degrees, right? Degrees. Okay, it would approach 0. Whereas on the opposite end, as the rays, the sun rays that are hitting the equator have what kind of degrees, what angle? They're approaching, and they're actually going to be at 90 degrees. What is the larger? And then if you move, extrapolate into the south, the same phenomenon occurs in the south, right? And now the angle reverts to the other side. So do the angle of incidence continue to increase going south? No, if you're going to south, you have to reverse. So the angle of incidence starts getting smaller and smaller again, okay? But in the southern hemisphere. So where do you have the largest value, the largest angle of incidence, the largest value? At the equator. At the equator, it's going to be 90 degrees. That's the largest it can get, because then as it moves south, it's going to start narrowing down again. Okay, it's going to start doing this, right? Following? Okay.
Basis for like latitude, is that why? Or is that something else?
Well, the latitude is simply artificial lines drawn around the orange, okay, horizontally, so that we can measure also degrees, but those are degrees from the core, from the center of the Earth. So degrees north, degrees south, that's latitude. This is a different angle. This is on the outside. Latitude is an inner angle, all right? And then you have longitude around the orange, around the surface, starting at Greenwich, 360 degrees around, all right? So latitudes actually have only 90 degrees. From the equator to the pole is 90 degrees north. From the equator to the south pole is 90 degrees south, okay? But longitude going around is 360 degrees at Greenwich, through UK somewhere, around. All right, forward. Now, let's put it together in the real system. Yes. Here's our sun, because it is so far away, not because it's so far away, but because it is so much larger than us, than the Earth. The surface where the rays are leaving, the sun rays are leaving toward the Earth, is practically flat. It's for all purposes flat. So that's why we consider these rays essentially coming in as parallel to each other, all right? So what is causing the equator to be warmer than the poles, or conversely, the poles to be colder than the equator? It's not this distance, because this distance is not to scale. This actual distance is not to scale, okay? Even the two circumferences are not to scale. Let's say if the Earth were to this scale, right? If the Earth were this size, this would look what? A solid wall, okay? Straight up, because 100 to 1, we could not detect. In this short distance, we could not detect that bend. It would seem as if it were flat. You get it? Please get it. Okay, stick with me. Right, it's rather because of the angle of incidence. The bottom line, the difference in temperature is because of the angle of incidence, all right? In other words, the greater the angle of incidence, the more heat there's going to be, because the rays are bouncing off almost backwards on a mirror. And that causes, there's more concentration of rays, if you will. The surface that is being hit proportionally is smaller at the equator than at the poles because of that angle. okay? And because the surface is smaller, you can think of it as a concentration. If you have the same amount of rays, 3 rays here and 3 rays here, and these 3 rays at the equator are illuminating and therefore heating up a smaller area than these 3 rays over here near the poles that are illuminating and therefore heating a larger area. Proportionately, the smaller area is going to get more hot than the larger area because you have the same amount of light and therefore the same amount of light to heat conversion. Remember that anytime a light hits a surface, a photon hits a surface, some of that photon is degenerated into heat. It generates heat. That heat will then dissipate passively, right? So it's that energy conversion. If that energy conversion happens in a smaller area, proportionally, it's going to generate more heat than if those same rays hit a larger area. Proportionally, there's going to be less heat generated over there in the second area, in the larger area. So it's all about the angle of incidence that makes the poles colder than the equator, or vice versa, the equator hotter than the poles. Okay? Of course, what's implied behind here in the background that is not really said by the diagram is that these light rays, these photons, when they hit a surface, some of those photons are going to be reflected as light, but other is going to be transformed. There's an energy transformation into what? What have I been talking about? Heat, into heat, okay? When light hits the surface, some of that light is going to be transformed into heat, all right? Okay. That's what makes the poles colder than the equator, or vice versa, the equator warmer than the pole, even if the actual equator is tilted a little bit. Anyway, let's move forward, and there's another little, we need to understand this because you see how here's in an idealized Earth, this is for the sake of illustration or pedagogical reasons. The Earth is put here as vertical, even though there is a slant on it, but for the purpose of illustration, the Earth, to keep it simple, the Earth is put vertical, all right? The axis of the Earth is vertical. You see how it's warmer, is shown warmer at the equator, and with a color, with the red color, because I associate red with warm, we associate blue with cold. So we're going to look now, because this is going to be the basis for these Coriolis. For first, the convection. Coriolis is going to be a combination of 2 forces. First, convection, the convection currents, but on a spinning sphere, on a rotating sphere, which is going to make that convection to twist. All right, so there's going to be it's a combination of a vertical movement on the atmosphere and a horizontal movement at the surface of the Earth. Is going to make that convection current twist and cause the weather patterns. Okay, let's go for it. Little video here, 3 or 4 minutes.
This animation, we're going to look at global wind patterns and talk about the reasons why the air circulates the way it does, and also patterns of rising and sinking air and how that relates to vegetation. The engine that drives it all, I guess you could say, is the intense heating by the sun that occurs only in the equator areas, where the sun is shining at a very high angle of incidence.
High angle of incidence.
Hot air near the
90 degrees.
Less dense, rises upward. It rises upward and it moves toward the poles, and then it gradually sinks at about 30 degrees north of the south latitude. So you create these big spinning circles of air that we call it Hadley cell.
Hadley cell. Therefore, low pressure. L, low pressure. Okay. At least for me, in my brain, this is counterintuitive because I associate the tropics with it's high heat, but it's low pressure. The air is rising. These cells, he just mentioned it briefly, Hadley cells, because he's the fellow who discovered it. Hadley cells, don't worry about that. But they have a name. All right. So you see how they form, and this is the first, and this is going to be 30-degree latitude, by the way. North, and this is 30-degree south. And this is equator, 0 degree, okay?
Now, near the equator where the air is rising, it loses its ability to hold moisture and you get up to end of high rainfall and low pressure because there's air leaving the equator. Where the air sinks in these belts at around 30 degrees north and south, you get high pressure sinking air, which creates areas of clear skies and desert climates. Now, as this air circulates and tries to flow back toward the equator along the surface of the Earth, or as some of it heads toward the North Pole or toward the South Pole, the Coriolis effect, the spin of the Earth, causes it to bend and turn, and it's going to create two big wind belts that prevail on our Earth, 2 out of 3. The trade winds, northeast trade winds and southeast trade winds, and then the prevailing western. Now these winds curve in the way they do because of the Coriolis effect. Winds curve to the right of their path, north of the equator. They curve to the left of their path, south of the equator, and they end up going from east to west, or from west to east. Now the other big factor is what's happening at the poles. At the poles, the air is cold, and the cold air wants to sink. And as that cold polar air sinks, it heads toward the equator and it bumps into this air heading toward the pole here and toward the south pole here. And it creates an area of rising air, and again, rising air produces high precipitation belts at about 60 degrees north and about 60 degrees south latitude. At the poles themselves, the precipitation is quite modest because the air is sinking, and that creates low precipitation.
Okay.
Would that be the temperate rainforest?
Yes, exactly. That's right.
It's simple.
Actually, the coniferous rainforest.
Everything we do.
Okay, right.
Coniferous rainforest, right? And that's why it's so lush up there in the boundary, pretty much around the northern swath of the U.S. into Canada,
And Russia too.
and Russia and Siberia, that whole belt from what is essentially Canada and then Siberia is a coniferous forest that gets a lot of humidity and rain, and it's very high vegetation because it gets plenty of rain, plenty of water. That's around more or less the 60 degree latitude, north, south. The only problem with south is that there's very little landmass. It's mostly the Pacific Ocean or the South Atlantic or the Indian Ocean, but whatever little landmass there is, yes. In South America, down toward Chile, but mostly Argentina, and then the southern tip of Africa. And then the whole Polynesian Islands, of course, very lush.
Which islands?
The Polynesian Islands, moving toward the South Pacific. Okay. All right, so that was the explanation for the Coriolis effect. Again, the name for the fellow who discovered this way back. And it causes that counterclockwise rotation in the northern hemisphere and clockwise rotation in the southern hemisphere, which is very, very evident in the formation of hurricanes and even storms. But then you have these bands at the equator. They have the equatorial low, and then the trade winds just north and south of the equator, which are good winds for sailing, by the way, have been used for centuries by migrating routes, the trade winds. And then you get into the westerlies from 30 to 60 degree, north and south, and then on the opposite side are the easterlies. And then the subtropical, subpolar low, and finally the polar high on both sides. So you see it's a combination of vertical movement caused by, what's the main factor of the vertical movement of the atmosphere? And I'm talking about the troposphere mostly. Convection, right? Which is driven by, what's the energy drive of the convection? Heat. The effect is lower pressure, and then higher pressure as it condenses and so forth. That's one movement, which is vertical generally. And then the other movement is the rotation, the spin, the rotation of the Earth around its axis, which is going to cause a horizontal movement on a plane. And the combination of those two is the Coriolis effect, which causes essentially the weather pattern for the whole Earth, all right, in the big picture. One last video explaining this conserved spinning momentum, because this lady, she's going to mention conserved spinning momentum just in passing, but let me explain it briefly first so you can understand it. Remember the ice skater, all right? And she's rotating on the tip of the skate, which is a steel blade on ice, right? And first she runs, or he, doesn't matter, but the skater will then go on the tip and take that momentum, that horizontal momentum of the run, and pin it down literally on an axis. And so that spinning momentum is going to now translate into a rotating momentum, because the person has stopped running on a linear fashion, but carries momentum, carries energy, right? So that translates into a spinning momentum. That's known as the angular momentum. But that person spinning now on the tip of the steel blade of the skate fixed upon the ice, right, has mass. And because it has mass on the surface of the Earth, it also has weight. The weight is the pull of gravity upon mass. And so he or she can literally play around with the speed of momentum by either extending or contracting the arms. Because then when she extends the arms, that mass of her arms are further away from the axis. So it's kind of dissipating mass, if you will, or redistributing the mass into a wider spin, okay? But when she pulls her arms in, that mass is being concentrated toward the center. So proportionally, there's more mass near the center, near the axis, and that mass is going to react more to the gravity and makes her spin faster. So she can literally change her speed by extending or contracting her arms, or the skater. Okay, and the leg also can do the same phenomenon. One leg, because the other leg is fixed as a peg on the ice. All right, that's known as the angular momentum, and is conserved. Conserved means that that speed continues, the momentum continues when there is no friction. Okay, and that's where there is a difference. I'll come back to that point, but let's look at the video. There's a similarity between the skater spinning and the Earth spinning, but there's also a difference, okay? I want you to think of what is the similarity and what is the what is the difference in physical terms. That was a chalk.
If you've ever watched the news during a hurricane or a wintertime nor'easter, you've probably noticed that big storms spin over time as they travel. In the northern hemisphere, they spin counterclockwise. Yeah. But if you were watching a storm in the southern hemisphere, you'd see it spinning clockwise. Why do storms spin in different directions depending on their location? And why do they spin in the first place? A storm's rotation is due to something called the Coriolis effect, which is a phenomenon that causes fluids like water and air to curve as they travel across or above Earth's surface. Here's the basic idea. Earth is constantly spinning around its axis from west to east. But because Earth is a sphere and wider in the middle, points on the equator are actually spinning faster around the axis than points near the poles.
More distance to travel.
So imagine you were
in the same time
Texas and had a magic paper airplane that could travel hundreds of miles. If you flew your airplane directly northward, you might think it would land straight north, maybe somewhere in Nebraska. But Texas is actually spinning around Earth's axis faster than Nebraska is, because it's closer to the equator. That means that the paper airplane is spinning faster as well, And when you throw it, that spinning momentum is conserved. So if you threw your paper airplane in a straight line toward the north, it would land somewhere to the right of Nebraska, maybe in Delaware. So from your point of view in Texas, the plane would have taken a curved path to the right. The opposite would happen in the southern hemisphere. An object traveling from the equator to the south would get deflected to the left. So what does this have to do with hurricane spinning? Well, at the center of every hurricane is an area of very low pressure. As a result, the high pressure air surrounding the center or eye of a storm is constantly rushing toward the low pressure void in the middle. But because of the Coriolis effect, the air rushing toward the center is deflected off course. In the northern hemisphere, the volumes of air on all sides of the eye keep getting tugged slightly to the right. The air keeps trying to make its way to the middle and keeps getting deflected, causing the entire system to spin in a counterclockwise direction. In the southern hemisphere, where the Coriolis effect pulls air to the left, the opposite happens. Storms spin around the eye in a clockwise manner.
There it is. Formation of hurricanes in 2 minutes or less. So it's all about this Coriolis effect. And oops.
I took prize there because I wanted to specialize in something.
Good. Right? So now you know why the hurricanes then spin counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. The last thing, the only difference is why does the skater eventually stop spinning? Friction, exactly. There's friction, and there's two kinds of friction affecting the skater. The most obvious one is where? Exactly, right here at the point of skate, that blade touching the ice is actually causing friction. Slight friction, but real, all right? So eventually, the resistance of the ice to the blade is going to slow down the skater eventually, all right? So there's friction there. There's another friction also because the skater is rotating, right, with the spinning momentum, and it's rotating where? Not in a vacuum, but in the air. There's air around the skater. So that air is also going to offer some slight resistance. The air immediately around her is going to spin with her. But as you move away from her body, literally, the other air tends to be, it's in its place. It's not moving around, not as much, especially in an enclosed area. And so there is resistance. Those molecules are actually frictioning against each other and slowing each other down. So the combination of friction of the blade on the ice and her body on the air mass around her will eventually make her stop, okay, make the skater stop. And that's the difference with the Earth, because the Earth is rotating around its axis. Where is that axis fixed on some kind of hypothetical plane or some kind of ether that the Earth is spinning on? No, it's spinning in space. It's a vacuum in quotations because actually there's all kinds of energy and waves going through it, so it's not empty as such, but it's, and even there is even matter there, but the distance between the molecules in space is gigantic, thousands of kilometers far from each other, so it's essentially no friction for the spinning of the Earth, and that's why it continues to spin and it hasn't slowed down. Okay, other things can affect it, like wobble, for example. That's much more significant and dangerous for us. So you notice that the Earth spins on its axis, right? And the axis is tilted, but also that axis is beginning to wobble. In other words, it's beginning to do this. I'm exaggerating, but it's not just spinning on its own like a top. You know, we used to play tops when I was a kid. I used to play tops, right? But that top, when it slows down, it starts angling and it starts wobbling. And that's what's happening to the Earth. Axis is starting to wobble. that has all kinds of consequences. One major consequence is that eventually it may just spin out of orbit, okay? We don't know, in a few hundred millions of years, in a few billion years, the space will spin out of. We're not going to be here, we're going to watch it from somewhere else, but if we follow that film forward, that's one of the fates, possible fates of Earth, like other planets, to either spin out into space or to spin in and eventually collapse into the sun and disintegrate way before we actually touch the sun, just from the intensity of the heat and the radiation. All right, so this is the final, oh, I think this one is actually a repeat. Let's see, GUKE. Yeah, this is the same video. Yeah, this is the same video that we saw. It just explains, so here you see, okay, now finally you see the Hadley cells. There's a full pattern here of all the Hadley cells. It would be essentially 3 on the north hemisphere and 3 more in the southern hemisphere, with their convection current movement and then the lateral movement because of Coriolis effect, and that's what generates the whole wind pattern of the Earth.
So in the western region of trade winds, is there less wind? Is that?
Yes, it tends to be, it's normally known as a subtropical region, and that's pretty much where we're at. Florida goes right, we're here, I think we're about 23, 24 degrees north, right, latitude. 30 degrees just northern Florida, essentially, the boundary between Mexico and the US, more or less. So that's a low pressure system, and typically if you go away from the peninsula, what do you find in the mainland? Desert. Right? You got Texas, you got Arizona, you got, what else over here, New Mexico, that whole area. So it's a high pressure system, clear skies. And I'm sorry, what was the original question?
That's just the wind.
The wind?
Is it,
yeah.
It's just less wind.
It tends to be less wind, but again, the other issue is that these are global wind patterns, by which much more affected by the local wind pattern than the local, okay? And that has to do with the heating and the cooling of the day on a daily basis. So local wind patterns are much more significant for us because we're such a small scale. You know, when you get beyond 7 or 8 feet, we're not normally feeling it because we're a 6-foot person is a tall person. So anything that happens like 10 feet above us is not as, unless it has its consequences below.
So that would have more to do with the plane flow.
Yes, exactly. And they do catch, for example, you hear about the jet stream, right? They catch the jet stream because that's tailwind, literally, just like a sail, all right? Like a ship on the ocean, like a sail ship. If the sailboat has wind from the stern, it's going to fly with the wind, all right? And it's not really felt. I love sailing, and when you're in the sailboat, you don't really feel the backwind, the stern wind, because you're moving, the boat is moving with the wind.
It's always longer when you're flying northwest.
Yes, because you're going against the wind pattern,
so
exactly. That's right, the jet stream is going against you. And so coming back is a shorter, the same with Europe. Going over is faster than coming back because of the distance and the wind pattern. Reverse in the southern hemisphere. That's the last thing. Okay, so finally, just now we're able to distinguish more clearly between weather and climate, all right? Because weather is the phenomenon on the atmosphere on a daily basis. What's the most obvious one? It's so obvious that we don't even consider it. But what's the most obvious weather change, drastic weather change from day to day? Light or no light, day and night. It happens every 24 hours. It's pretty drastic between light and no light. Think of plants, for example, and animals. and so on and so forth. Okay, so that's the first weather change that is drastic. It happens every day, and we just kind of take it for granted. Light, no light. Of course, ever since we harness light and now have artificial light, it affects us less and less. But then that has all kinds of other consequences, because precisely because that light during the day is hitting the surface and a good amount of that light is being transformed into heat, then another consequence of day and night is hot or cold, warmer, colder. Warmer in the day generally, colder at night. Where do you feel that the most? The contrast between hot and cold on a daily basis or nightly basis. Give you an example. I'll give you in a humid region like South Florida, for example, or in a desert region like Arizona. Yes, desert. Why? Very hot during the day and very cold during the night. You go to the Grand Canyon, you got to take layers of jackets with you and sweaters, because at night the temperature drops 20, 30, 40 degrees. Is the pressure going to change significantly from day to night? No, but what does change? Whether there's humidity or not. This is the other silent or hidden factor. Humidity, which is what? Which is water, vapor, gas, water, H2O, which is, I didn't put it in the, because it's such a small amount, but significant. H2O, gas, floating around. Exactly, it retains heat. Water molecule has a high heat capacity, remember? So water retains heat, just like CO2. Now I'm kind of surprised looking back that it's not even on the table. It's so on the, where were we? It's so small, it's not even here. That's interesting. I'd like to look it up at some point. Where is H2O, vapor, gas? It's got to be in here somewhere, because that makes a difference between a tropical rainforest or a desert. Okay, both at the same latitude, one with water vapor, the other one without water vapor. And so water vapor, gas, H2O, that is here right now, and especially beyond this wall, it's pretty humid out there, right? On average, on a day. And that makes it warmer. But it makes it warmer, actually, it makes it cooler during the day, because it's actually that water vapor is absorbing heat, and therefore there's less heat, let's say, available. Water vapor makes it a little bit cooler during the day and warmer during the night, because that water vapor sticks around, all right? And therefore it provides heat to the local atmosphere. And so the night feels warmer here, for example, in South Florida, than it would in the desert. In the desert, there's much less water vapor, right? And therefore during the day, that heat dissipation that happens from light bouncing off, reflecting off the surface, that heat is just available for our bodies to absorb it and make us feel hotter, because the water, there's no water vapor around us, or very little water vapor. And so proportionally, it's absorbing less heat. So our bodies proportionally is absorbing more of that heat that is just around, okay, in the natural oven. But at night, because there is no light, there's no transfer from light to heat, and therefore it's cold. And because there's no water vapor to embrace us and to protect us and to give us warmth, then we dissipate our own heat. We're endotherms, and we dissipate our own heat and we feel cold. And that's what's happening physically, why we feel warmer in the desert and colder, warmer during the day, colder at night, than we do over here in a humid atmosphere. Okay? So, you know, and it's not here. I need to complement this and find out what's the water heat, the water vapor capacity content. So anyway, we're looking at weather. It's what happens on a daily basis in the atmosphere. So we got, we talked about pressure, which is pretty much standard wherever we are on Earth, all right? As long as we are at sea level, but if we move altitude, which is the third component of the cube, right, x, y, z, so we got latitude if we go north or south on the surface of the Earth. We got longitude if we go east-west on the sphere, but then we can also go up or down mountains. That's altitude, right? And that means we're going, let's say we're going higher on the troposphere or lower on the troposphere on those 10 kilometers of air that we have on top of us. That makes a difference. We go up higher on mountains, there's proportionally less what? Less atmosphere in general, so therefore for us significantly less oxygen. And so that's why in high altitude, when athletes run or do their sports, they feel tired faster because they have proportionally less oxygen. And that's also why runners go up to the Colorado mountain range, to the Rocky Mountain range to train because they're building vigor, they're building stamina up there where they're being deprived of oxygen, okay? And then they come down here and they have an overabundance of oxygen. They're intoxicated with oxygen. In fact, literally, if you go to Israel, and it's one of the crevices of the earth, all right, but it's not flooded with water, so one can walk there, but it's below sea level. The Dead Sea, right, and the shore of the Dead Sea is literally below sea level, maybe 100 feet or something like that. It's significant. I don't know exactly how much, but the atmosphere, of course, pours down in there because it's going to hold the volume of the container, and there's more oxygen down there proportionally, and so you can get actually intoxicated if you run fast or start doing exercise. You're pumping in excess amount of oxygen in your body, and you start getting dizzy and feeling equivalent to nitrogen necrosis and feeling kind of groggy, because there's an excess of oxygen below the surface of the earth, below sea level. All right, but that's all weather systems. So you got the humidity of the air, you have the light, you have then just the normal weather, whether it's raining or not. Then the cloud friction on the surface of the earth causes charges, positive and negative charge, which then is going to release that charge periodically, and that's called lightning, thunder or lightning. Just like at night when you do your blanket, you go like this with a blanket, especially if the air conditioning is down, so it has sucked out the humidity from the air, right? You go like this with a blanket, you see all the little sparks, okay? Those little sparks is static energy that is being released. And those are mini tiny lightnings, or natural lightning is huge, humongous little sparks, okay, of static that are being released to the tune of tens of thousands of kilowatts of electricity going through. All right, so it's some of the largest charges and discharges of electricity going through. And it's basically release of static. So these are all the local weather patterns that occur in a relatively small area on a daily basis, on a weekly basis, on a seasonal basis. You bring it up to a whole year, right? The 4 seasons in the temperate region, and so on and so forth. So even up to a year, you can have a varying weather pattern. It's still weather, even on a yearly basis. Climate is different because climate then is long-term, typically measured in thousands of years or even millions of years. Okay, and that's climate. So when we talk, one thing is to talk about weather change. Weather changes every day. Climate change is a different story because climate change is long-term, minimally thousands of years, and typically hundreds of thousands or millions of years. So it follows geologic time scale. Okay, so when we talk about climate change, we have to put it in quotations because then we have to do modeling because we haven't been around with instruments to measure climate. We've measured weather in a relatively small period of time, like maybe with actual instruments, maybe 200, 300, 400 years maximum. Beyond the Industrial Revolution, we just didn't have the instruments, maybe into the Renaissance period. And then we have to rely on indirect measurements, which are what? core samples of the ice and so on and so forth. What happened to the atmosphere? How much CO2 accumulated with burning forest or who knows what? But it's an indirect measurement. So what happens? Getting into statistics and prepping you up, the margin of error for that data is going to increase. More or less percentage of margin of error because we are now not measuring directly, but indirect measure. That's going back historically. Going forward, we have zero instruments. What we're doing now is mathematical projections. Based on what? Based on history. So the more data we have, it's interesting how it dovetails right into stats. The more robust the database, the better our predictive models. But they're models nonetheless. And every model, sooner or later, is doomed to fail. We call it adjusting. We have to adjust the model as we go along. But basically, the prediction is off target. Now, the off target could be significant if we're shooting a rocket from here and plan it to land on Mars hundreds of thousands of miles away. The angle of incidence and the angle of arrival can make a big difference, all right? Because a tiny fraction of a fraction of a fraction of a second of difference. Remember? 60 minutes in a degree and 60 seconds in a minute, and then it goes into the decimal system. A very tiny fraction of error in the angle of that projectile, when you run that for hundreds of thousands of miles, it's going to miss the target altogether. Okay? It's going to be way off target. So there have to be adjustments along the way. Anyway, so climate is long-term, and that's the big unknown there. And that's where it can get political and ideological because they're models, okay? And literally, pardon the pun, but models will be spun to a particular ideology depending on what, and that's why it's so important that science has to be, you know, empirical means it doesn't exist unless it can be measured, okay? And so this thing really doesn't exist unless I can measure it. That's empirical science. And that's the issue that we have as scientists with this whole claim of climate change, because we also know by looking at the history that in the past 500 million years, there have been at least 4 or 5 ice ages. 5 ice ages where the whole Earth has been either tropicalized or winterized. And I'm talking about, this is a good photo here actually, or a good model, a good caricature. Tropicalized, when the Earth tropicalized, it means that up here in the Northern Hemisphere, which is most of the landmass, is a tropical rainforest. We actually have evidence for that, empirical evidence that can be measured. What's it called? The residue of the tropical rainforest, fossil fuel, petroleum, gas, and coal, fossil fuels. What is fossil fuel? Rotted forests, okay? Decomposed forests that have been compressed into gas, natural gas, into liquid petroleum, guck, and into solid coal. Where is all that? Well, around the rim of the North Pole. Alaska has petroleum, Canada and Siberia, right? In fact, in Europe, where are the oil fields of Europe? In the Northern Sea, which is really the Northern Sea is the North Atlantic already into the Arctic Circle. Petroleum there. Why? Well, because those used to be tropical rainforests. Oh, but below sea level, yes. And in fact, the sea level was even higher back then, maybe 100 to 200 feet above us when the ice caps were melted. Okay, that's tropical ice in the Earth. No North Pole as ice because there's no continent there. And the South Pole, exposed rock, right? Antarctica, the continent that is down there. And so the sea level was higher. So what? Well, that just means that the shore goes inland into the continents, but it also allows for the entire northern hemisphere to be vegetated instead of today that part of it is tundra because it's permafrost and therefore the roots cannot penetrate that solid ice below the surface of the Earth. Okay, So huge tropical rainforests in this area, at least 4 times that have been known. And in the meantime, and through several 100,000 years, and then cycles of cold and warm. So in the winter ice, the ice sheet has actually come down just above Florida. Okay, there's evidence of ice sheets all the way down into southern US here, and certainly across the Europe into the Mediterranean and Asia. So essentially, a good section of the northern hemisphere, certainly most of the landmass, covered with solid ice. And I'm talking about, again, 100 to 200 feet of ice. I'm not talking about little ice cubes here on the surface, okay? Sheets of ice, miles, moving back and forth for hundreds of thousands of years, just scarring the surface of the earth back and forth to the point of making the Great Lakes, carving out the Great Lakes, which are some of the deepest lakes in the world. All right, the 5 Great Lakes between US and Canada. That's climate, and that's climate change. And that's measured in hundreds of thousands of years, and we had zero to do with that, right? So that's why we have to put it in perspective. What we can ask is, what is the human factor possibly contributing to climate change? That's the bioethical question. And in addition, and aside from climate change, contamination, pollution of material stuff, which is happening independently of the CO2 rise in the atmosphere, which also has its own bioethical questions, all right? So just putting this, this thing in perspective, many people really don't think because it's warmer this year than it was last year, that's weather, really, that's weather. Now, and that in a long time scale is called noise. It's noise, it's just fluctuation going back and forth. But we have to look at what's the slope of the line, what's the trend, all right? If it's a positive trend, if it's neutral, or if it's a negative trend. And that actually gets us into probability and statistics. So this is a good point for stopping. All right, questions, comments, anything?
So it's still considered weather even if you're measuring, let's say, like 100 years? You're still calling that weather?
Yes, because then we can talk about weather patterns that start contributing to our climate. And certainly each tick on that line is a data point, all right? But it's the trend, it's the trend. So weather patterns do contribute to climate trends. And that is on a daily basis, on an hourly basis. All right, I think we're ready to stop this then. So I'm gonna stop the recording, and to the folks who logged in, thanks a lot. I'm gonna stop this now, and we'll see you next time. Oh, actually, you know what? Let me pause recording because I don't want to lose you folks if you want to be on the session. Okay, so I'm going to pause recording for a moment.